So in this presentation we have to talk about the fundamentals of XPS. At the earlier stages, XPS is known as ESCA, electron spectroscopy for chemical analysis. With the help of this XPS analysis, we may know the elemental composition of a material and oxidation state. We know that oxidation is the liberation of electron, reduction is the gain of electron. So for example, Zn is a neutral atom. If Zn emits 2 electrons, we can get Zn2 plus cation. This is the example for oxidation. Now consider oxygen atom. After absorbing 2 electrons, this oxygen atom is converted into O2 minus ion. This is an example for reduction. In a chemical reaction, if there is an increase in oxidation state, that is known as oxidation. Whereas if there is a decrease in oxidation state, it is known as reduction. Say, increase in oxidation state means the oxidation number is positive. Decrease in oxidation state means the oxidation number is negative. Then the negative oxidation number is called as reduction. But generally we are speaking, during the oxidation process, electron is liberated. During the reduction process, electron is gained. Say, in the case of ZnO, the oxidation state of Zn is plus 2. At the same time, the oxidation state of oxygen is minus 2. This means that Zn is ready to accept 2 electrons to form a chemical bond with oxygen. Zn 2 plus O2 minus give Zn O. Now we may go to the mechanism involved in XPS process. During the surface analysis by XPS, the interaction of surface atoms of the material with the incident low penetrating power X-ray emits electrons by the photoelectric effect. See, X-ray removes the electron from the K shell. This is a photoelectron. Suppose a substance is taken for our consideration that should contain more and more atoms, so more and more photoelectrons are coming out of that particular substance. The peaks obtained using the binding energies of the emitted photoelectrons against the emission intensity provide the XPS result of the sample. See here, binding energy versus intensity of the emitted electron will provide XPS spectrum of the sample. Now, how do you calculate the binding energy? That is the question mark. According to Einstein photoelectric equation, the energy of the incident photon h nu is used in 2 ways. Part of the energy is used to remove an electron from the substance, and the remaining energy is supplied to the electron as kinetic energy. See, this h nu 0 is part of the energy used to remove the electron from that surface, and the remaining energy is given to the electron as kinetic energy. Say the incident photon energy h nu, that is energy of the X-ray h nu, is used in 2 ways. This is our photoelectric function pi. H nu 0 is replaced by pi, then half mv square is the kinetic energy given to the electron. So h nu is equal to pi plus half mv square. Now the binding energy of the electron is h nu minus of pi plus half mv square. Binding energy means energy possessed by the electron if it is present in a particular orbit. As we know, an electron in the K shell has higher binding energy than an electron in the L shell. See here, this is K electron. The binding energy of the K electron is more than that of the binding energy of the L electron, because the K electron is present closer to the nucleus. So the interaction with the nucleus is more for the K electron when we compare the K electron with our L electron. Once the incident X-ray removes an electron from the K shell, a vacancy is created. Here, the incident X-ray removes the electron from the K shell. As a result of this removal, a vacancy is created. To fill the vacancy, an electron from the nearby L shell may make a quantum jump to the K shell. Here, an electron from the L shell is making a quantum jump to this spot. As a result of this transition, a photon is emitted. During this transition, a photon is emitted. If emissions of photons fill all the K shell vacancies, then the number of K electrons knocked out will equal the number of K photons emitted. See, the system contains more and more atoms, so more and more K electrons are coming out as photoelectron. In order to fill up such vacancies, electrons from the L shell are making their quantum jump to the different K shells. That means the K shells correspond to different atoms. In this way, we may expect more and more photons. The number of photons coming out as a result of this transition should be equal to the number of electrons coming out of different K shells. But in actual practice, that is not equal. See here, as a result of this transition, a photon is emitted. If emissions of photons fill all the K shell vacancies, then the number of K electrons knocked out will equal the number of K photons emitted. But experimentally, the number of photons emitted does not equal the number of electrons knocked out. The vacancy in the K shell can be filled by another process called Auger transition. In this process, the K shell vacancy can be filled by an electron from the L1 subshell, and an electron from the L2 subshell may be knocked out, resulting in two vacancies in the L shell. The non-radiative process is known as the Auger transition. Now see this diagram. Suppose an electron is knocked out from the K shell, a vacancy is created. In order to fill up this vacancy, an electron from the L shell may make a quantum jump. As a result of this quantum jump, energy is liberated. This is one type. But in the case of Auger transition, without any emission of photon, the vacancy is filled up by an electron from the L1 shell. At the same instant of time, another electron from the L2 shell, that means L2 subshell. Here L1 shell is s orbit in the L shell, L2 shell is the p orbit in the L shell. Another electron is automatically coming out of the system. The transition of this type is called Auger transition. During this Auger transition, no radiation is emitted. Now read out this. The vacancy in the K shell can be filled by another process called Auger transition. In this process, the K shell vacancy can be filled by an electron from the L1 subshell. That means an orbit of L shell. See here, this is s orbit of L shell. And an electron from L2 subshell may be knocked out. Here L2 subshell means p orbit of the L shell. An electron from the p orbit of the L shell is automatically going out without any radiation emission. This is called radiationless transition. The non-radiative process is known as Auger transition. Now this is the XPS of ZNO. spin orbital splitting of 2p level. To understand more about this, you should know this table. Here n stands for the principal quantum number, n equal to 1 corresponding to K shell, n equal to 2 represents the L shell, n equal to 3 represents the M shell. The number of electrons in each and every shell is given by the formula 2n square. Here n is equal to 1, so the number of electrons in the K shell is 2. For the L shell, the value of n is equal to 2, so 8 electrons are present in the L shell. For n equal to 3, the relevant shell is M. In the M shell, 18 electrons are present. Now this table represents the orbital angular momentum quantum number L. Suppose the value of L equal to 0, the orbit is named as S orbit. If L is equal to 1, the orbit is named as P orbit. L is equal to 2, the orbit is called as D orbit. The total number of electrons in an orbit is given by the formula 2 into 2L plus 1. Here L equal to 0 represents the S orbit, so S orbit may have only 2 electrons, because if you put L equal to 0, 0 into 2, 0, 0 plus 1, 1, 1 into 2, 2. If you put the small l, that is orbital angular momentum quantum number, is equal to 1, that represents the P orbit. P orbit may contain 6 electrons. In the same manner, the D orbit can have 10 electrons. We may extend our process in the similar manner. Now consider this K shell. The maximum number of electrons in the K shell is 2. For the K shell, the value of L is equal to 0, because for the value of n, L can have 0 to n minus 1 values. Suppose n equal to 1, the possible values of L is only 0. Suppose n is equal to 2, the possible values of L are 0, 1. So n equal to 2 represents our L shell. The maximum number of electrons in the L shell is 8. These 8 electrons are distributed in S and P orbits. S orbit contains 2 electrons, P orbit holds 6 electrons. So 8 electrons are distributed in S and P orbits. In this way we may explain the rest of the things also. Now come to this spectrum. 2p orbital splitting, spin orbital splitting of 2p level. This is for Z and O. In the case of Z and O, spin orbital splitting of 2p level is arrived. This is XPS spectrum of Z and O. Now, the x-axis represents the binding energy of the electrons, y-axis is the intensity. Spin orbital splitting. See here, the p orbit is separated into 2 compartments. One is 2p 1 by 2 and another one is 2p 3 by 2. Here 2 represents the principal quantum number n. N is equal to corresponding to L shell. Here P represents the orbital angular momentum quantum number L is equal to 1, because L equal to 0 represents the S orbit. P stands for L is equal to 1. Here the orbital angular momentum quantum number L is equal to 1. The 1 by 2 is our J. Here J equal to 1 by 2. In this case, N is equal to 2. P represents the orbital angular momentum quantum number, that is 1, but J equal to 3 by 2. So in this case, J is our total angular momentum. We are considering J is equal to L minus S option. Here we are considering the value of J equal to L plus S. Say L is equal to 1, the value of S is 1 by 2. So 1 minus 1 by 2 is 1 by 2. Here L is equal to 1, the value of S equal to 1 by 2. 1 plus 1 by 2 is 3 by 2. Say J equal to L minus S is one possibility, J equal to L plus S is another one possibility. Suppose L and S are parallel. This is called as spin up state, which means that the value of J equal to L plus S, that is 3 by 2. If L and S are antiparallel, orbital angular momentum quantum number and spin are antiparallel, is called as spin down state. In this case, we have to select the option J equal to L minus S, that is equal to 1 minus 1 by 2 equal to 1 by 2. See that the binding energy of spin down state is always greater than that of the binding energy of spin up state. See this 2p 1 by 2 is having higher binding energy, that is 1045 electron volt. The binding energy of spin up state, that is 2p 3 by 2, is always lesser than 2p 1 by 2. See this is lesser than 1025, but here the value is 1044, but the value of 2p 3 by 2 is 1021.4 electron volt, but the binding energy of 2p 1 by 2 is 1044.6 electron volt, which means that if you think about the spin down state, that means an electron which is antiparallel with the orbital motion, the binding energy of that electron is more than that of an electron which is parallel to the orbital angular momentum, that is spin up state. Once the binding energy is more, that electron is not coming out of the system easily. Therefore, if you concentrate on the intensity wise, the intensity corresponding to the spin down state is lesser than that of the intensity corresponding to spin up state. See here, the electrons with the spin up state are coming out more in number, but electrons with spin down state are coming out with lesser in number. So the intensity of the P corresponding to 2p 1 by 2 state is always lesser than that of the intensity of the P corresponding to 2p 3 by 2 state. There are 2 points we have to keep in our mind. One is the binding energy corresponding to spin down state is always greater than that of the binding energy corresponding to spin up state. And another one point is the intensity corresponding to spin down state is always lesser than the intensity corresponding to spin up state. Once the binding energy is more, only less number of electrons are coming out of the system, because high binding energy electrons are having more affinity with the nucleus. In this way, we may interpret the spin orbital splitting of 2p level of ZNO. With the help of these binding energies, we may conclude that the Zn in ZNO is in the Zn2 plus state. With the help of the binding energies, that is spin orbital splitting, we may come to the conclusion about the oxidation state of Zn. To know more about XPS analysis, we should discuss with some other spectra. We will continue the same in the next lecture. Thank you.